Welcome to the fourth lecture, the 6th week of the course in machine learning. In this lecture we will talk about learning mechanism in a multi-layer ANN. That's backpropagation mechanism. So actually this is the last lecture in a series of 3 that is concerned with feed-forward networks. Learning in feed-forward multi-layer ANN is handled by a mechanism called backpropagation, and this lecture is going to be focused on that mechanism. The terminologies are somewhat confusing. Here we stick to feed-forward multi-layer ANN, and we are saying that, for example, that a perceptron is a single-layer ANN. However, there are some people who talk about multi-layer perceptrons when they talk about multi-layer ANN. So there are these terminologies around, but we are going to stick to the version chosen here. So backpropagation is a generalization of the delta learning rule for single neurons. Backpropagation is shorthand for the backward propagation of errors. That's very important to make things clear. So an error is computed at the output end, at the output layer, and distributed backwards throughout the network's layers, which is simply what's going on. This backpropagation is based on the chain rule to iteratively compute the gradients for each layer needed in the calculation of the updates of the weights for these layers. So, as you will see, updating of weights is very similar to the single neuron case. Forward feeding is also very similar. What's different is the way these errors estimates are backpropagated. And essentially, backpropagation is a special case of a more general technique called automatic differentiation. And essentially, automatic differentiation is a set of techniques to numerically evaluate the derivative of a function specified by a computer program. So we are dealing here with a function expressed in terms of a computer program. And this exploits the fact that every such program, no matter how complicated it is, really executes a sequence of elementary arithmetic operations and elementary functions put together in a typically recursive manner. So by applying the chain rule repeatedly to this complicated function expressed by this recursive structure, derivatives of arbitrary order can be computed then automatically, accurately, and efficiently. But this is a general mathematical technique, and what we see in backpropagation is just a very specific instance of it. Let us now look at the combined feed-forward and backpropagation mechanisms in this kind of network. So first, of course, the structure of the multiple layer ANN have to be specified, including inputs and outputs. Then all the other parameters have to be set in place. So for example, the biases, normally modeled as extra inputs, activation functions for all neurons, the learning rate, etc. have to be specified. So then, for every round of computation, for each data item, we define the input values and the target value. Yeah. So feed forward takes place, as we have seen it earlier, across the network using a single neuron model, and there is no difference here. We calculate the sum of the weighted inputs. If that sum exceeds 0, including, of course, the bias, the handling of the bias value, then the output value is calculated as an activation function of the sum. Otherwise, the value is 0. And then then this is done systematically through all the layers in the network. So when we come to the end, we compare the target value of this specific data item with the output value and multiply that with the derivative of the transfer function with respect to the weighted sum. So this happens in the end. So step 2 here is what happens to the output end of the network. After that, we come to the backpropagation phase, which actually we backpropagate the errors across the network using exactly the same ways as we use for the feed-forward phase. So the feed-forward phase are based on a current set of weights. We calculate the error sensitivity value to n, and then using the same weights as we had, we calculate the error estimates backwards through the network. So when that's done, actually, and we got these error estimates for every node of the network, then we can update the weights, and that we do in a very similar fashion to what we did in the single neuron case. So we take the old value of a weight and add an expression, which is the learning rate times the error estimate at this point times the derivative of the transfer function with respect to the weighted sum, and multiply by the input value for that connection. So sum up, everything is very much the same in the single neuron case. The only thing is the forward feeding have to be carried out all through the network, and there is a backpropagation of error phase followed by an update of weight phase, which is also according to the single neuron case. I'm now going to show you a simple example of the machinery of a feed-forward multiple layer network. The intention with this example is primarily to exemplify the cycles including feed-forward signals, backpropagation of errors, and adaptation of weights. In order to keep it simple and show you the principles, there are a lot of simplifications made for this example. So, for example, we have an activation function, which is an identity function, which means the gradients become trivially 1. We have a learning rate of 1. We disconsider the biases and so on. So what we have here is a network with 2 inputs, 1 output, and 6 other units organized in 3 layers. What I'm going to show you now is what happened in the, I would say, 4 phases that we have of this process. The first phase is the feed-forward phase. So essentially we can see that the values, input values are propagated layer by layer, and outputs are calculated in each layer. So you go from the left to the right, and then you can see in the end an output value is calculated in the end. In this phase, we use a certain setup of weights, which are either the initial ones or inherited from an earlier phase. And this calculation is performed as in the single neuron case for each of the neurons. Next phase is that when we reach the end, we calculate this value, which we call the error sensitivity measure, which is simply the difference between the target value and the output value. And having done that, we can start what's really the backpropagation. So what we do then is that we calculate a similar value for each of the nodes, for each of the neurons, moving backwards, utilizing exactly the same weights that we used in the forward phase. So this phase is over when we got a error sensitivity measure for each. When that is done, we can move to the last phase, which is the recalculation of weights. And actually, the recalculation of weights can be done locally for each neuron according to, in principle, the same kind of formula that was used for the single neuron. So to summarize here again, the big difference with backpropagation, the big addition, is the backpropagation of errors. You are probably bored by now by backpropagation, but I will take the risk to give you a new version of an example. I guess you have heard that repetition is the mother of all learning. So here you find an example with figures, it's just symbols. So here there are also the three phases. So the feed forward phase, where we feed input values, we have an initial setting of the same weight for every edge weight all over the network, and we calculate the output value through all the levels up to the end. And then we have the backpropagation phase, where we take the error sensitivity measure and feed it backwards. And here you can see that we calculate that estimate for all the neurons. When that is done, then we can do the adjustment of weights according to by now familiar formula, and you can see this is done throughout the network. This is a local computation, so that is happened to each neuron, so the order is unimportant. There is a feed forward, there is a backpropagation, and then there is a local weight update at each unit. The weight for the last two for the last two connections are eliminated here, and it will be saved as a problem for you to solve in the assignment. I now want to share with you an analogy to backpropagation in NAL. And the analogy is with the area of genetic algorithms classifier system. I hope you remember that we talked about that some weeks ago when we talked about different kinds of representations. So in the genetic algorithm classifier system area, there's something called a bucket brigade algorithm. So a classifier system is a rule-based architecture where the adaptation of the rule base is based on a genetic algorithm architecture. So in genetic algorithm terminology, a rule is considered as a gene in the gene pool and is automatically provided with a fitness value. The fitness of a rule decides its destiny in the DNA selection scheme. So the fitness value, of course, is very important for a rule to survive in this evolution of the rule base. So in the fashion of reinforcement learning, the outcome of each problem solving is provided with a reward, can be compared to an error value. What happens in this kind of system is that you want to decide which rule that contributed to the solution should be given some level of credit or blame. But the problem you have is you have a reward at the end. So the credit or blame is like given at the end of the process when you have a solution. So then people devised, Holland and Associate, something called the bucket brigade algorithm that actually moves backward from the totally from the end of the problem solving and hierarchically following all the rules backward, exact more or less in the fashion that we do in a neural network. And what this bucket brigade algorithm does is that it recursively allot awards for a particular rule, and then, of course, forming the basis for the updating of the fitness of that rule. So viewing what's happened in backpropagation and viewing what happened in this kind of system, I mean, formally there are details that differs, but abstractly the algorithm has the same purpose. Finally, before I end this lecture, I like to mention a few specific approaches that are examples of feed-forward approaches. My main reason for doing that is that some of these specific methods you may meet if you continue with this area. When you look into specific applications, these will be mentioned because those I take up have been successfully used in various kinds of applications. So my purpose here is, so to say, for your benefit, put them in the right basket, so to say. The first one I want to mention is something called radial basis function network, which is actually a very simple network with one hidden layer, one input and one output. What's specific is that the middle layer has a very specific activation function, which is a radial basis function, and you can see to the right examples how such function looks like. Actually, the input layer is very simple. It's just a fan-out layer and has no processing. The second example I want to give you is something called autoencoder. And actually, Dowding is also a feed-forward, non-recurrent, so we are still in the genre, but with the possibility to perform not only supervised but unsupervised learning. So this kind of network can have several hidden layers, and the main aim of this kind of network is dimensionality reduction. So this means that you have input which are described in too many in a feature space with too many dimensions. You can use this kind of component to reduce the dimensionality and also improve the sensitivity to noise. Also, this kind of network has been used for reconstruction of input with only partial characteristics of objects. This was the end of this lecture. Thanks for your attention. The next lecture, 6.5, will be on the topic recurrent neural networks. Thank you.